So, good morning. First of all, let me wish you all a very happy Vijayadashmi. It's a very auspicious day to start with a new chapter of learning. At least Indian traditions do say that. Yes, now this talk addressing the maths aspirants is in their expert talks series. I don't know whether I can call myself an expert on this, but certainly I have some experience which I can possibly communicate to you during this talk. The theme of this talk is something very general. It is not something very sophisticated mathematics or anything. But what I want to do today is to introduce to you a beautiful book written by a great mathematician, G. Polya, entitled How to Solve It. And this is a book which I believe that every student of science and even of humanities should read. Secondly, it's also something the teachers of science, especially mathematics teachers, should, at all levels, should read. Not only that, through your communications with the students, you should convey the main aspects of this particular book. Because it will make a phenomenal importance, a phenomenal change in the attitude of people towards mathematics, and mathematics would become far more friendly. And right now it has a sort of a reputation that it's a dreadful subject. Mainly because many people do not understand what goes on. And Polya's efforts had been to decode this aspect. Let me just give some more introductory talk about this little book. It appeared in 1945, and Polya had been looking at how people solve problems. This is not something new to all. I mean, in fact, right from the days on which you have come on earth, you have been solving problems. You have been coming across problems, and then sometimes or quite often you fail to solve problems, but then at some stage or other your persistent efforts, if you make it helps you to solve a problem. For instance, you could have watched how a small baby, not even able to walk, is trying to climb steps. Initially it is going to fail, or it may even fall down. All these experiences are there, but then there is a moment when it would possibly sort out the problem on its own, or by himself or herself, and that's a moment of triumph. And one of the great virtues of human mind, maybe true also for many animals, is that once you do something, you have it, especially if you do it all by yourself, it will be etched deep in your memory, and it is stored, and then you recall it and use it on other occasions. And your cognitive mind is capable of correlating various ideas together and then even recalling the sort of knowledge that you have developed in the past and then use it at the right time. Now, this is something very fascinating about the human mind. Now, I have often thought that, see, all of us do solve problems, and how do we do this? I mean, this is the question. Just probably you are not aware of all the steps that your intelligence carries out in solving the problem. This is a fact. And that's why sometimes you feel that you have a sort of revelation at some stage of a method that you can use to solve the problem or even the solution of the problem. This happens suddenly and you have a feeling that you have solved the problem, and others do not understand how you solve the problem, nor you are able to explain to them how you solve the problem. Then everyone thinks that, oh, you are a genius, somehow or other things come to your mind. But then I am certainly sure that this is not how your intelligence has worked. It has systematically analyzed the problem and solved the problem. Quite often, these actions happen in the subconscious state of your mind, not in the conscious state of the mind. Had it been in the conscious state of the mind, I think you would know how you have solved it, you would know each step that you would have taken to solve the problem. But when there is a gap, you feel that a lot of things, or it is true that a lot of things have happened in your subconscious mind. That means you are working with your problem, maybe doing other things also simultaneously because you do a lot of multiple tasking. And I think maybe an analogy with the modern computers would make things slightly clear. Well, you see that you can make your desktop or laptop to grapple over several problems at the same time, at least a handful of different problems at the same time. Only one of them is that you open on your screen and you are consciously looking at it, but other things may be getting solved by in the background, which you may not be aware of. Eventually you get a signal when the problem is completely solved, you get a signal and then open that window corresponding to that problem, you will see what exactly is the solution. This kind of activity happens in your brain also, I believe. I mean, I don't know, I have not read this anywhere. This is what I have experienced, or I have even felt about this kind of activity. So this analogy should make it clear what exactly is happening in your subconsciousness. Because in the subconsciousness you are solving the problem, you are attacking the problem, you are always thinking about the problem, and it is getting all the various options are being weighed, analyzed, and then a way out is found. And probably when the way out is found, suddenly you are just reminded of a sort of mode of solving the problem or a way of attacking the problem into your conscious mind, and then you start probably pursue that path and get the problem solved. Now this is what happens. Therefore, what happens is whatever has happened in your subconscious mind is not even known to you, or you are not able to recall it. You are not able to clearly say what it is. At that stage, you feel that there had been a revelation, sort of what you call, I got a magnificent idea, all of a sudden. And how you arrived at this idea is a question that is not clear. In fact, what Polya has done, let me come back to Polya. What Polya has done in this beautiful book is possibly to tell you what goes on in your mind, in the background, how you would have approached the problem, and then he probably devises a kind of a protocol for solving any problem. Now this is the aspect of it. Okay. So what do you do? How do you approach a problem? How do you solve the problem? Now this is the main theme of this particular book. Polya says there are 4 different steps to solving the problem. The first one is understanding the problem. We just open the window. Okay. Is understanding the problem. Two, devising a plan. The third step is carrying out the plan. And then fourth is looking back. These 4 vital major steps are there in solving any problem. I don't know whether you do it these days, but we had a first encounter with I believe the logical mathematics while doing classical geometry and the theorems in geometry during the school days. There, if you had done it, otherwise this is what you do. The first thing that you look at on a problem is what is the unknown. Essentially, what exactly you want to prove? You should have some clarity on that. And then, of course, you ask, what is the data? So, these 2 things have to be first of all sorted out. What exactly you want to prove or what you want to achieve. I will just make a word about research towards the end, but right now you are given a problem and that's a presumption. So the unknown is known and there is a certain amount of data that is given, and what are the conditions? Okay. These 3 things have to be very clearly understood. There should be no mixing up of the 2 things. You cannot really mix up these kind of things, because if you do that, then if you don't have clarity on what is that you are searching for, and what are the premises on which you are standing, and then what are the conditions under which you are working, then the problem cannot be solved. In fact, quite often your subconscious mind will be doing this. Initially it may not be clear, but later on at some stage or other, once you sort out this, then you are going to link up these various things, because your job is from the given data you have to get to the unknown under these conditions. These are the conditions. So under these conditions you have to get there. Now this is the status of any problem. Your day-to-day life problem or mathematical problem or anything. Now the best examples had been my first experience of doing such things systematically came from classical geometry when you were to prove certain theorems. Okay, right? For example, you take the problem that you have a parallelogram. One of the results that you have proved or you are familiar with is that the opposite angles are equal, and then the opposite sides are equal. Okay, so what is the unknown? The unknown is that you are given a quadrilateral, a four-sided figure in a plane with a certain condition. What are the conditions? It's not free. This is not true. The statement is not true in all quadrilaterals. But the condition is that you see that it's a parallelogram. That is the data. Okay. So a quadrilateral is given, which is a parallelogram. So that gives the given data and the sort of conditions that you have. So it's a quadrilateral that is given, and the conditions that are further imposed on that, it is a parallelogram. Then the conclusion that you want to make is that the opposite sides are equal, opposite angles are equal. Even more can be concluded from this, that okay. Right, there are so many other results that you can prove associated with the parallelogram. So I think you got an idea of exactly what the problem is. I am taking a very simple problem so that it is easily accessible to you, no sophistications. So the clarity about what is that you are seeking, on what premises you stand, and under what conditions you are able to achieve that. This is the first thing to be sorted out. Okay, that's understanding the problem. Now, how do you approach a problem? When you have a sophisticated problem, how do you approach or even arrive at this kind of conclusions? You see that you draw a lot of quadrilaterals under these conditions of different sizes. In all this, probably you measure the length of the sides, measure the angles, then you observe that they are the stated conclusions do hold. Okay, now your task is this: how to get from the known or the given to the unknown. That is what you call solving the problem. Okay, you can put every problem that you see in your mathematics text in this particular language. The first thing that you need is the clarity of what is the data, what is the unknown, what are the conditions that are there, and then probably from here you devise a method to go from the unknown to the go from the given premises to the expected result. Okay, so this is the first step of understanding the problem. Now, how to see? There are various exercises that you can do on this. As I said, consider different examples. Okay. Verify. Now the examples may be trivial, simple examples, to more sophisticated examples. In fact, it's always advised that you start with something very simple and then slowly progress to increasing complexity and then take examples and try to sort out this problem. And you see there are some stages, in some cases it may be obvious, but later on there are some cases where it may not be obvious. Okay. The second thing that you do is, can you restate the problem in your own words? That means you come to a more friendly understanding of the problem or realization of what the problem is the moment you translate into your own languages. You can draw some pictures as I did here. Okay? Or in some cases it is possible to draw a picture, in some cases it may not be possible. Or maybe a diagram that might help you to understand the problem. Now you analyze, do you have sufficient data to come to the conclusion? Now this is what I said, that you check on various examples whether the result is true or not. Or do you have to change the problem slightly or reword it in such a way that you can understand it better? Now this is one of the primary tasks of solving a problem. So the first step is to distinguish between the unknown, the data and the conditions. Okay. What happens next? The next step is to devise a plan. This is where the actual solving process starts in your mind. What one does at this level? You ask some interesting questions. Have you seen this problem before? Or have you seen a problem which is quite similar to this? And if you have already seen a similar problem, what did you do in those circumstances? Is there any way to improvise that to solving your new problem? I'll just give a very simple example. You have a rectangular parallelepiped, a box. You draw the box. Now suppose the sides are of length A, B and C. That is, A is the length, B is the breadth and C is the height. Now you look at the diagram. Okay. Look at the diagram. The main diagram. Main diagram will be the line joining the opposite corners, something like this. The question that you have is, what is the length of main diagram. How is it related? Obviously, your common sense tells you that probably you are able to relate the length of this diagonal to the sides, the data that is given, namely A, B and C. There are a few things in the data. What is it? It's a rectangular parallelepiped. It's a box. Now you look at all the diagonals. All the diagonals have the same length. Okay? Because it's a rectangular parallelepiped. Otherwise, no. For instance, in a general parallelogram, you see that the two diagonals have different lengths. But the moment you are considering a rectangle, the diagonals have the same length. Okay? So that is also availability. Therefore, it is enough to know the length of one of the diagonals. Then you know the length of all the diagonals of the parallelogram. Okay? But the problem is, how do you solve this? So the major question that you ask is, have you seen anything like this? Any other problem? Yes, this is a pertinent question that you can ask in all circumstances. Have you seen a similar problem? If you have seen a similar problem and you know how you have solved it, then it is very simple. Not very simple, but as you can see in this problem, that probably the method that has been used to resolve that problem can be improvised in this scenario. Okay, what did you do? You know that in the case of a rectangle, you know that you have the Pythagoras theorem. It says a square plus b square equal to the c square. Well, the c is the length of the diagonal. So that is the Pythagoras theorem. That you know. Yes. Can you use it here? Because at the outset, no. Why? Because that is valid in the plane, but you are working in a three-dimensional state. Okay. So either you can drop this problem and feel happy or unhappy about it, or you can go ahead further and ask deeper questions. Can you use the method that you have used this problem? So the problem is, can one reduce the problem to maybe you need a few constructions. What you do is you have a hard look at your figure that you have already drawn. Had it been in a plane, as a plane figure, then you would have had the solution. You could have directly do this. Therefore, is it possible to reduce this to using this result? This is what I said. See, the human beings have the rare gift or blessing that if they have solved a problem, then it is there in their, it is stored up somewhere. And once it is stored up, then possibly if you are sharp enough, you can recall that at the right moment and then use it. So can you reduce this problem to doing that? Okay, I think the answer is clear. You draw the diagonal of the base. Now the diagonal of the base is, the length of the diagonal of the base is, now you are with the usual Pythagoras theorem. It is square root of a square plus b square. Fine, you got this. So what? So this is an ad hoc step that you have introduced in your problem to facilitate using the known fact. Now what you have? You immediately make an observation that the diagonal that you want to compute is essentially the diagonal of another right angle triangle or another parallelogram. Another rectangular parallel, another rectangle. Which is the rectangle? The rectangle has this side, this is one side, this is another side, and then of course you have got, this is a rectangle. Okay, so it's a diagonal of that. Or you have a triangle here, which is a right angle triangle, where you can use your Pythagoras theorem again. So what you have? You know the height of the rectangular box, and this diagonal you know already, you have already computed. Now it is quite simple, and the answer is a square plus b square. That's the length that you are seeking. So what have you done here? We have used the results of a known problem, or you have recapped your experience, past experience, and devised it to solve this particular problem. Now this is one of the steps that you often work out. Okay, it is not that once a problem is given, it is always you are always able to solve this. Okay, then what do you do? Okay, you ask questions like, can you solve a related problem? Can you solve a problem with further conditions, namely than what is already available to you? I will give an example. Take the parallelepiped. First realize that your rectangle is a parallelepiped. Okay. Now can you, here you see that under the assumption that the parallelogram is a rectangle or a right angle, a rectangle, can you prove this theorem? So what have we done? We have brought in an extra condition. Now you want to prove in this case that the opposite sides are equal. Okay? Is it possible? This is the problem. So what one does is this. First of all, you observe that both the diagonals have the same length. I mean, forget about that. That is not relevant here. Okay? But you know that all the angles are equal to one another. Whereas in a general parallelogram, they are not. Only opposite side angles would be equal. And not all the four angles are equal. Here all the four angles are equal. Therefore, this is certainly a special case, but not every rectangle, not every parallelogram is a rectangle, but every rectangle is a parallelogram. Okay? Therefore, let us first prove the things for this particular case. Now, what one does is you can use the what is called equivalence of triangles. So you take these triangles. Now you see that this is a right angle triangle. Okay, so this particular angle is equal to this particular angle. Okay. And this is a common side. Okay. Now what more you can work on? You can see that these two sides are parallel. That is a conclusion that you can draw, because these two lines are divided by a line, have the same angles, and the sum of these two angles is pi. Okay, so these two lines are parallel, and then this is a line that cuts it. Therefore, you have these two angles equal. So there are two triangles where two angles are equal to one another, and there is a common side. Then they are congruent, and the congruence essentially tells you that these two sides are equal. I mean, there are many ways in which you can argue it. But what I wanted to say is that once it's a rectangle, it is much more simpler than this. Okay. Now, having solved this, so with only one extra condition, you have solved this. As far as you are concerned, only this revised or redesigned problem satisfies your requirement. But is it necessary to have all the inner angles to be equal to solve this problem? Or can you generalize this? Now you see, a generalization would give you, all that you need is, you need only the opposite angles equal, then you can write down the proof of this. Okay? So that really solves. In fact, you use a string of theorems to connect all these things and then prove this result. Okay? So that's a very simple thing to do, and I am not going into the details. So if you are not able to solve a problem, you go to a related problem. If you are not able to solve the problem with the data, given data, then you put some extra conditions and try to solve it. And then, after solving that, possibly you are able to take out these extra conditions. Okay? So that's a two-step or even several-step solution to your problem. This is one of the methods that you resort to. In your mind, you will be working on with all these things while solving a problem. Any problem for that matter. Now you often use in mathematics, this is very clear, in other case also, this is actually converting one problem into another problem. Okay. Transforming a problem into another problem. So that your original problem will be solved if you have a solution for the transformed problem. The two are equivalent. Then the solution of one problem gives you the solution of the other. This is the important thing. Now I just give a very interesting situation from ordinary differential equations. You would have seen those who have done first order ordinary differential equation with an initial condition yx not equal to y naught. I am not making a very precise statement of the problem. How do you show that this equation has a solution? That means there exists a function z of x over some interval such that z derivative at x is equal to and of course at x naught z of x naught equal to y naught. This is what you mean by a solution of this problem. One thing that you observe is this. You can convert this problem into another problem. What do you do? Integrate it. It's all crude methods that you use. Finally, you can make them look very rigorous. You see that if you integrate from x naught to some x on both sides, then you end up with this. This is what you get. Have you solved the problem? No. Why? Because y is involved under the integral also. If that is not there, then you would have solved the problem. A given function integrated would have given you the solution. But that is not the case. Y is sitting here, y is also sitting here. But what have you done? You have transformed the problem to solving another problem. Why? Because if you check, if you put x equal to x naught, then you get yx naught minus yx naught equal to 0, which will give you this condition. This is y naught. Okay. Further, you can justify, differentiate on both sides, then you end up with this. Therefore, this differential equation or initial value problem leads to an integral equation. And this integral equation is equivalent to the initial value problem that we have. Therefore, solving this problem is done provided you solve this problem. So you have converted one problem into another problem. This is a technique that one uses so frequently in mathematics. If you are not able to solve a problem, you convert this into another problem where you can solve it equivalently. Or even go for a problem with further conditions so that you are near the actual problem. And this is something that you do. Now, you do all sorts of, see, at the stage of solving a problem, you don't bother about the rigor. That's the last thing that you do. Okay? You don't have to be obsessed with that. You can do all sorts of things that make some sense to transforming, differentiating, integrating, all the tools that you know can be used. I mean, every spanner and screwdriver can be used to unlock, lock, and all these things. And this is what you do. So you have got, in mathematics, what I say is a mathematician is like a technician. Okay. Suppose you have to fix a problem on a car. What do? You go to your shop. Go to your shop, then you see those who have gone to your shop and seen they would have a huge board on which the spanners and screwdrivers are kept of different size. You say 12 inch, 2 inch, 3 inch, then probably 5 inches or 8 inches. This kind of various spanners are kept, and then what the technician does is he knows he doesn't have any problem. What he does is he looks at, he listens to you about the problem, then he makes up in his mind what would be the plausible reasons for such a hold up. Then he will come with pick a few spanners from there, and then possibly a few nuts and bolts, etc. Then he will start unscrewing something and then refixing something. But he doesn't have to think too much because of his familiarity. He doesn't have to think much about which spanner is to be picked. So, as in a mathematician's workshop, all the results that have been proved are this kind of spanners and screwdrivers, which you have to use at the right moment. You might ask, there are scores of such results. You might ask which theorem to be used, and this comes from your experience. This comes from the understanding of the problem, and the understanding of the problem, like an expert workshop technician, you will be hitting upon the right kind of tools or right kind of theorems that you want to resolve your problem, and that comes from your deep experience. Therefore, understanding the problem is the most important part, and that leads to what kind of tools you have to use to fix the problem. Okay, I mean, whatever I say today, you can think of while you yourself solving the problems. And I would suggest that even known problems you try to solve consciously and analyze every step. That is the best way to learn mathematics. The best way to learn mathematics is solve problems. And there is no shortcut. Absolutely no shortcut. No one can teach you mathematics. I think no teacher, see, there is a saying, famous saying that mathematics is learned by doing it and not by watching others do it, which clearly tells you that no teacher working on a board and you are happily watching what is going on is going to make you a mathematician. It's like swimming. Without, you can give a lecture on swimming, what one should do, etc. But with that, if you enter a pool, you are not able to float yourself and be drowning. Okay? So you have to have the experience. And your experience in a pool by learning swimming, you will be drinking a lot of water, lot of dirty water sometimes, depending on the status of the pool. And this is unavoidable. Okay? And you do a lot of mistakes, and from the mistakes you learn something. Each mistake is a stepping stone for some further understanding of the problem. So, don't hesitate to handle a problem. Don't be discouraged by seeing the mistakes that you do. Each mistake is a blessing. And if you easily pass over a trouble spot, then probably you won't observe what is happening. But if you get stuck there, then there is a chance that you will be observing more deeply what exactly is the problem, what exactly is the difficulty, and how one overcomes that. So these are very, very important things while solving a problem. And then what one does is, the third step is actually carrying out a plan. So in your mind you devise a plan and then carry out the plan, which should involve all sorts of computations, figure drawing, some sort of additional constructions that you do, etc., etc. And then you arrive at a solution. Okay? And finally, having solved a problem, it's not that always you are able to solve a problem. Having solved a problem, you ask, you review the entire steps that you have gone through to solve the problem. You don't leave it at that stage. And the review will make you much more, proficient and understanding, and allow you to understand the problem much better and the devices that you have used to solve the problem better. And you can ask a next question. Sometimes you will be using a very, very long and lengthy path to solve a problem. So that's the way in which you would have resolved the whole thing. And having solved the problem, you could ask this question: is it possible for me to do it in a much simpler way? Possibly. Having so much understood, with so much understanding of the problem, maybe you are able to find a much better path or much better way of resolving the problem, or even more than one path to resolve this particular problem. So all these are a part of a design, and I would certainly invite you to carefully read this book, How to Solve It. He gives some beautiful examples. The examples I have given are not exactly what except this particular one. Other examples he uses from various aspects of mathematics, and just gives a glimpse of how exactly you resolve this problem. And I think I have about 8 minutes to 12 o'clock. That is the time where I have to stop talking about it. I told you something in the beginning, that possibly in the path of research, how you go. This is again my experience. You would have seen natural sciences. How do the theories come out in natural sciences? You have experiments. Okay? From experiments, you collect data. And then the next step is, look at the patterns that are hidden in the data. And from there, a theory evolves. So, data collected in the form of experiments as well as observations are extremely important aspects of a scientific venture. Okay? And the collected information would stay far ahead of the theory that you develop. And then based on that, the theory is developed. And quite often you see that many theories fall flat, because when further data is collected, sometimes it will fail. Your theory fails to explain that out. Then you discard the theory and go for a worthwhile modification of this. Okay, what is the analogy with mathematics? In mathematics, the analogous thing is working on examples. Okay? And it's often said that if you have a beautiful example where computations look magnificently elegant, or there is a rare beauty about the solution of that problem, then the suspicion would be that there is a incredible structure that works behind it. I'll give a very simple example. A simple example is this. Look at look at a square matrix. And you see that you can talk about the determinant of a square matrix. And then of course, very curious way in which you compute the determinant. And you can see that this is, where do you come across that? Equal to suppose you want to solve this problem. When you work out the solution, you will see that invariably you will come across what is the determinant of A, B, C, D, and this itself can be recast into which gives much better transparency. Can you get a given a vector alpha beta, can you find xy such that this is true? The problem comes to inversion of this. If you can invert this matrix, then you can easily write down the solution. If the inverse exists, then this is going to be xy equal to A, B, C, D alpha beta. This is the solution, provided the inverse exists. Now you see that if you work out the solution, actually your classical way of working out the solution, you will come across what is called the determinant. That is AD minus BC is not equal to 0 is the statement equivalent to ABCD is invertible. Okay, right. This is what we call the determinant of ABCD. Now this has been used right from the time and people use this determinant to have a more compact notation, etc., etc. And then of course the properties of the determinant was analyzed in detail. Like if you have two columns equal, then they are 0. If the two columns are interchanged, then the sign changes, etc., etc. All these properties are there about this determinant. But you see that it's a very curious way of working it out. You are multiplying like this. It is still worse when you come to A, B, A1, B1, C1, A2, B2, C2, A3, B3, C3. The way in which you expand or write down the determinant, although the notation is simple, it's more complicated. Okay. So people naturally ask questions, why do you make such a complicated expansion of this? Of course, in this context it works. But otherwise, can you not define determinants in a different way? Well, you can do that, but you may not have as elegant properties as possible. But it so happens that this particular expansion rule, which is so complicated, has such a nice properties. Then what is it? Then you see that this has a beautiful structure that works behind this. And that I don't have time and or probably to explain what exactly it is. You can devise this as there is a analogous vector space of dimension 1 of n alternating forms, which is of dimension 1, and the determinant appears to be a scalar multiplication of the linear alternating forms. Okay, so that's the result. So you see, there are some beautiful computations taking place, then you should always suspect that there is some nice structure behind it. And in research, you have to speculate what the problem is. The first one, what is unknown, that you have to speculate. How do you speculate? Look at the experimental data, the analogs of that, the problems that you have solved. From there you speculate what is unknown. So the problem itself is not known until you solve it. It may not be even true sometimes. So you will have to do a lot of grappling with the unknown itself, and you will have to devise a problem, and the problem that you devise may not be the right one. You may have to modify it, and you may have to arrive at a meaningful problem and then solve it as a part of your research activities. Okay, with these words, I think let me conclude, and I am grateful to my student Professor Vinod and Professor Biju for inviting me to talk to you this morning on an auspicious day and possibly tell you something about some general mathematics with you. And I am available for the next half an hour easily or even longer for further discussions. And I think we will move on to the Google Meet platform to solve this problem. So thank you very much. Okay, this is available on my channel. Anytime you want to have a further look at this, you can go to that. And in fact, there are nearly 195 lectures lying on this. So I too invite each one of you to have a look at it. Those students of mathematics and teachers of mathematics at the PG level should certainly benefit from the lectures I am giving. Right now, I am in the midst of giving a series of lectures on linear algebra. Thank you very much.